We begin the overall discussion on multipath fading channels by introducing the two-ray multipath model, which forms the basis for understanding many of the multipath phenomena that we encounter, including periodic deep fades and the depth of the deep fades, and also the spacing between the deep fades that are all related to the multipath delay, and also the amount of attenuation of the reflected multipath in a two-ray model. So in this section we will actually go ahead and derive some formulas that go a long way towards explaining what is going on in a two-ray multipath model. Here we show a multipath situation. We have the main ray from the transmit antenna to the receive antenna, and we have a reflection shown in the red. Usually the reflection will be of less power than the main ray. If we express this in a time domain and assume that the transmitter is sending an impulse, this is idealistic. Typically you're sending a carrier or a multitude of carriers, but for analysis purposes assume that you are in fact sending an impulse. Then the receive antenna receives S of t equals delta t, which is the main ray, plus an impulse delayed with tau d, which is the time difference between the main ray and the reflected ray. Obviously there's going to be a time delay between the two. And alpha, which is an attenuation of the reflected ray compared to the main ray, alpha less than 1. And they add up at the receiver. So the receiver is a combination of the main ray and the reflected ray expressed as delta t plus alpha delta t minus tau d. Note that in this case we are ignoring the bulk delay. So there is a bulk delay from the transmitter to the receiver and also from the reflection, and we're just ignoring that and just showing that the impulse has no bulk delay in order to simplify the expression. Now, what we need to do is analyze this, and the best thing to do is analyze this in the frequency domain. So in the next step, we'll take the Fourier transform of that expression. It's very straightforward. The Fourier transform of a impulse is a constant 1. And of course the impulse delayed by tau d is just e to the j 2 pi f, which is frequency tau d. And of course alpha is the attenuation. So this is the frequency response with multipath available. Now what we need to do is expand this, the exponential. So we expand exponential in terms of the cosine and j sine, and then we actually collect terms and compute the magnitude. So we're interested in the magnitude square of the frequency response, and we see that it's this expression that is highlighted in red. And as you can see, this expression is very interesting because it has a cosine term which is periodic with respect to the actual delay of the reflection. This is very interesting. Let's go ahead to the next step and we'll plot that out. So here we are actually plotting the frequency response, and you can see that there is a periodicity. The separation between the points where you actually have a dip is delta f, which is the inverse of the time delay. This is going to be very important. And we've actually highlighted where you have a dip, and the depth is related to, which is shown there, is related to alpha, the amount of reflection. If the reflection is in fact very large and on the order of the main ray itself, the dip actually becomes 0, so you have complete attenuation at that point. The less the reflection, the less the dip, the less the amount of distortion. So two things affect here. One is the amount of the reflection and of course the time delay itself. The larger the time delay, the worse the situation, the more the depths actually bunch up together. And sort of like a banjo, you have a very negative effect, more the fades, deep fades. And if the delay is smaller, then you have less of these within a bandwidth, and you could, of course, have a better situation. We're going to see a lot of this later when we talk about how to model an office environment. So to summarize, multipath does create a big problem. Depending on the delay, you have fading situations which bunch up together if, in fact, the delay is large, and you have less of them if the delay is smaller within a bandwidth. And the depth of the fade is dependent on the magnitude of the reflection. The larger the reflection, let's say off a barn or something that reflects the ray with a lot of power, then of course the fade will be deeper, and the more the attenuation and more the problem. In this section, we will discuss multipath fading channels which are encountered in wireless communication systems. Here we show a small office environment, and as you can see we have cubicles, various obstruction. If you had a AP and you had a station that was receiving and transmitting information to that AP, you may have line of sight and you have obstructions and you have multiple reflections off the walls. In this case, the delay spread will be quite small. We'll talk about delay spread later. Here's a large office environment in which many factors come into play. The multipath channel that you encounter depends on where you are in the office environment. For example, in the case of a laboratory environment, you will have cases where there are no obstructions, so you have multiple reflections off the wall, and the delays are actually larger than in the case of a cubicle environment. And say you had an AP in this location here, then you would have multiple reflections within a bounded area, and the delay spread, or the RMS delay spread, which we'll give a definition of, would be much smaller than in the case of an open laboratory environment. For example, in a large warehouse environment, the delay spread would be very large, since the multipaths would be unobstructed and would be received with a higher power and, of course, larger delay. So you would expect to have a larger delay spread in a warehouse environment than in a closed office environment. In the lab environment, you might expect to have a larger delay spread than a closed office environment, as shown over here. Now, the multipath environment depends on where you are. Large hallways actually create a waveguide effect, and you have beams that scatter energy from the wireless communication link, and you have multiple scattering sources. You have shadowing effects. You have penetration, for example, through the floors to the lower floors, etc. So many factors will impact the fading multipath channel. In this diagram, we illustrate three scenarios. One is reflection and pass-through, which is what we've been talking about mainly. You have a signal which may be incident, for example, on a wall, and it is reflected back. And it's this reflection that ends up as multipath. You also have the signal penetrating the wall, so you have pass-through signal, which would exhibit some attenuation. Here we show diffraction, where the incident signal hits a wall or a partition, and you have the diffraction, which is a shadowing effect. So even though the signal might originate here, the obstruction blocks the signal. However, due to diffraction, you have a shadowing and energy is received behind the obstruction. Of course, diffracted signals are attenuated considerably. You have knife edge effects and so forth. We'll talk about those a little bit later. Another source of multipath is scattering. Here a I-beam is shown, and as the incident wave impinges on the I-beam, you get currents generated within the I-beam, and each one of those radiates out another wavefront. So you have basic scattering, and each one of these would be a source, so that in a multipath environment like this, even though the AP is over here, you could receive signals from any angle coming into the antenna due to the multiple sources of scattering, reflection, and pass-through, and of course diffraction over the partitions and walls, etc. I highly recommend reading this paper by John Stein, Indoor Radio Wireland Performance, that was published, and you can find that on the internet. Here we show the equation for free space loss. This is the equation that is used to determine their loss through free space propagation from an antenna. We're not taking into consideration antenna gain or any other factors, just as this is just the loss due to free space propagation. The loss is proportional to the square of the distance, so as the distance increases, the free space loss increases, and it is inversely proportional to the square of the wavelength. And if we express the wavelength in terms of the speed of light divided by frequency, then we get this expression over here. So we see that as the frequency increases, as you go to higher and higher carrier frequencies, your free space loss also increases. This expression down here is very useful for our application. It expresses the free space loss in dBs. The unit for D, distance, in this case is meters, and the unit for frequency is gigahertz. So, for example, at a distance of 1 meter, we have 20 log of 1, which is equal to 0, and at 1 gigahertz, we have 20 log of base 10 of 1 is, of course, 0, and we actually get 32 dB of loss. Now, a few points have to be made about the free space loss dependent on frequency. For example, you might think that by increasing frequency, you have a lot of free space loss and therefore a much lower signal-to-noise ratio, but you have to actually take into consideration the antenna gains. As an example, in a microwave link, even though the frequency is very high, because you can use smaller dishes at higher frequencies, the antenna gain could be quite high, and you can actually achieve quite a high signal-to-noise ratio compared to cases where the frequency is lower and you don't have high gains in the antenna because the antennas have to be extremely large. So you really have to take a number of factors into consideration and do a actual link budget with antenna gains taken into consideration and the environment and of course the frequency and distance. But this formula here is pretty useful in terms of getting a rough idea of the free space loss as a function of distance for a fixed frequency. For example, in our case, for 802.11a, f would be, for example, 5.2 gigahertz. This curve again from Stein is very important, and it shows the typical path loss at 2.4 gigahertz within an indoor wireless environment. The y-axis shows the normalized path loss, and the x-axis is the distance from the radiating source or the transmitter. And the numbers here are in feet, and of course we've shown the numbers in meters. So at, for example, 3 meters, we see that the loss is minus 55, and as we go to around 30 meters, the loss is at around, say, 75 dB or 20 dB loss. So typically for every factor of 10 increase in distance, we have 20 dB per decade or 20 dB loss, which is shown over here, going from minus 55 to 75. Now, if you had free space, a completely open environment with no obstructions, no cause for reflections, you would expect, obviously, to just have free space loss, which would be the case, for example, in a microwave link with it designed correctly, with no reflections, taking into consideration the Fresnel zone, etc. But in a typical office environment, the distance over which free space applies is very short. What happens is because of multiple reflections and attenuations due to those reflections, etc., you don't have line of sight necessarily, and the loss increases beyond a certain point at a rate of 40 dB per decade. And then beyond, say, 300 meters, you have obstructions, you're going through floors, multiple walls, etc., and then you have 60 dB per decade of added loss, so the slope increases. This has been derived from many empirical studies and experiments. Refer you to the references in order to get more details, but it's a good curve to have handy when you are trying to figure out what the loss is in a typical indoor wireless environment at 2.4 gigahertz. This is a very interesting plot based on actual measured data within an indoor wireless environment, and the reference is, it was actually published in 1993, Indoor and Outdoor Propagation Measurements at 5 and 60 gigahertz for Radio LAN Applications by Plattner and Prediger. So these are actual measurements. So on the x-axis we have frequency, and this is at 5 gigahertz, and the span is 100 megahertz during the measurement, and I'm showing actually the space here is 20 megahertz. So this would be occupied for an 802.11a channel, for example, which has a bandwidth of 20 megahertz. The attenuation is shown here, and the units are 10 dB. So we see that within a 20 megahertz bandwidth, we exhibit what you call frequency-selective fading. In this case, we have multiple deep fades and quite a bit of fading and loss within a wide range of carriers, or a wide range of the bandwidth. Over here, you might even have very deep fades, and if you had a signal with a carrier placed in this location, you would have almost a total loss of that particular carrier. So we see that multipath fading is a problem in communications, and we have to come up with a modulation schemes in order to combat multipath fading channel issues. OFDM is one modulation technique which addresses this problem. We will discuss it in detail and show that how you use multiple carriers that are orthogonal to each other and spaced very closely in order to transmit the signals in very narrow bands, so that within each band, the narrow band, you have flat fading instead of the case of a wide band where you have frequency selective fading. Here we show a case where we actually model a fading multipath channel in software, and we're showing the case for a RMS delay spread of 150 nanoseconds, and we'll explain the definition of the RMS delay spread. This is a typical impulse response you might encounter at 150 nanosecond delay spread, and this is, for example, for an in-phase channel. For 802.11a OFDM, we're dealing with complex modulation, so we would have both an in-phase and quadrature phase channel. And this is the impulse response. We see that we would have the main ray, and then as it gets reflected, it is attenuated, and as it goes through multiple paths, you get more and more delay, and as you get further and further away from the transmitter, you exhibit multiple reflections and attenuations, and we expect the amplitude of the impulse to decrease, and of course we get phase reversals at some points. Here we show the power delay profile. For the power delay profile, we plot the received impulse at a particular delay. We plot its power against the delay. And here's what we see for a typical multipath fading channel, is that the power delay profile exhibits sort of a exponential decay in terms of the power as we increase the delay. And that is expected, since as we move out in distance, the signals are reflected multiple times and attenuated, and their power reduces. Also, as the delay increases, that means you're getting further and further away from the transmitter, and you have path loss, which attenuates the signal, and as we pointed out, shadowing effects and obstruction. So that also causes the signal to decrease in power the further and further you get out in the delay, and you have this exponential decay in the power delay profile. If we go back to the impulse response itself, one way to model these impulses is that due to the random nature and the random nature of the environment and the multipath and scattering, each one of these impulses will behave across multiple realizations of the channel. They will exhibit a normal distribution so that they are Gaussian, and if you measured multiple impulses at a particular delay and measured the actual received signal at this point, if you created a histogram of those impulses, they would exhibit a normal type distribution. In order to model multipath delay spread in software, then, we would pick the impulses from a normal distribution, but we will ensure that the actual delay profile follows an exponential decay to model the actual environment you would encounter in an indoor wireless environment. These types of models have become very popular, and they do a pretty good job of modeling multipath fading channels, and can be used in design and simulation in order to check, for example, the robustness of the OFDM modulation and demodulation in terms of packet detection and also packet error rate over various channels with various RMS delay spreads. So here we're showing the power delay profile, where each point here is the received power at that particular time as a function of the delay. Let's make a couple of definitions. Again, here we show the impulse response at a particular discrete delay tau sub k. We obtain a amplitude alpha sub k, and we have, of course, multiple multipath arrivals as we show over here. So the mean excess delay is specified as follows. So the expected value of the delay is called the mean excess delay, and what we do is we take the delay at each point here, multiply it times the power, that is alpha k squared, magnitude squared, multiply times that, and then sum them over all possible delays and divide by the power, which is the sum of all the received powers, alpha k squared. This expression over here, that'll give us the mean excess delay. Now, very important for our work is the RMS delay spread. So that's the variance of the delay spread. So here we have the RMS delay spread is equal to, we take the mean of tau squared minus the square of the mean, and if we compute the square root, we get the RMS value. So that's the RMS delay spread, where the mean of the delay squared is defined as follows. So we take at each delay, square the delay times the power at that delay, sum them and normalize them by the total power, and we get the mean of the square of the delays. And it is the RMS delay spread which is the most important parameter we will be dealing with. Here we define coherence bandwidth. So if for a particular channel we can measure the RMS delay spread, which is done quite often in a lot of experiments in indoor and outdoor environments, they measure the RMS delay spread, then we define the coherence bandwidth as the inverse of the RMS delay spread. So if the delay spread is in microseconds, for example, we will get the coherence bandwidth in megahertz. Now there's this factor 1 over beta that we need to include, and the reason for that is the coherence bandwidth should be thought of as the bandwidth over which we have flat fading. And let's take a closer look at that. In this case, we'll use, for example, 5. Other values can be used depending on the environment. Let's take a look at that. So in these two plots at the top, we show the actual complex spectrum for a multipath channel, fading channel. And this is over a bandwidth of 20 megahertz, and this is a complex spectrum because in OFDM we're dealing with a complex modulation. Here we show the actual power delay profile for a delay spread of 150 nanoseconds for the same channel. Now if we take the delay spread at 150 nanoseconds and invert it, we get 6.67 megahertz, which we've shown over here. So the inverse of the delay spread, we get 6.67 megahertz. Over 6.67 megahertz, we exhibit frequency-selective fading. But these deep fades, as you see here, are the distance between them correlate well with the inverse of the delay spread. But if we want to have flat fading, if we divide this 6.67 by 5, for example, we get around 1 megahertz in which we get flat fading, and you can see that if you actually divide this section by 5. Over just the inverse of the delay spread, we get frequency selective fading. So if we were going to design a system in which on a per sub-channel basis you wanted to have flat fading, then we would need to actually have a coherence bandwidth with a beta factor equals to 5 or larger. In fact, in OFDM, we'll use even a much larger value for beta. So again, the 6.67 megahertz shown over here is the inverse of the delay spread, and using a factor of 5, divide that by 5 so that you can approximate flat fading within a subchannel. Otherwise, even with the inverse of the delay spread, you do get frequency selective fading as shown over here. Here we show the complex multipath channels frequency response for RMS delay spread of 50 nanoseconds. Here we show the power delay profile for 50 nanoseconds, and notice that the delay dies out around 500 nanoseconds as compared to the case where the delay spread was 150 nanoseconds, and we have multiple received power signals at beyond 500 nanosecond delay spread. For OFDM, a major point is 800 nanoseconds because that is the cyclic prefix or guard interval. And if you look at 150 nanoseconds, we still receive multipath from beyond 800 nanoseconds. But at 50 nanoseconds delay spread, we receive very little energy beyond 800 nanoseconds. Also note the inverse relationship for the coherence bandwidth in terms of the inverse of the delay spread. For a delay spread of 50 nanoseconds, the inverse of the delay spread is 20 megahertz. And if you use the beta equal to 5 and you divided this by 5, you would actually get 4 megahertz. And within the 4 megahertz, you would see you have flat fading. You don't have frequency selective fading. But again, a value of larger than 5 would be needed. So comparing these two, we see that the inverse relationship between the coherence bandwidth and the delay spread here. As the delay spread increases, we exhibit more frequency selective fading over a fixed bandwidth than in the case where we actually reduce the RMS delay spread. Obviously, this multipath channel would be much more of a problem in terms of reliable communications compared to the case where we have much less delay spread. Again, comparing the multipath fading channel response for 150 nanosecond delay spread versus 50 nanosecond delay spread, we see that we have frequency selective fading for the case of 150 nanoseconds. We also have frequency selective fading for the case of 50 nanoseconds, but we can use much less sub-channels in order to communicate over this channel versus the channel with 150 nanosecond delay. So in order to achieve reliable communication over fading multipath channels, one way to combat this is to take the data that we want to transmit and divide it up among sub-channels, as we show over here, and then send the data in each one of these sub-channels in parallel, and at the receiver we multiplex them back together to get our high throughput. And as each sub-channel would use less bandwidth, less data rate, then its bandwidth would be smaller, and within each sub-channel you would hopefully have a flat fading environment, so you won't have frequency selective fading. For the example we show over here, we still see that even if you use multiple carriers, within the carriers we do have frequency selective fading, so you would actually have to use many more sub-carriers or sub-channels. The next figure shows the actual case that is used in 802.11a. So over the 20 megahertz bandwidth, we actually use 64 carriers, each carrier carrying a number of bits, all of them in parallel. And the carrier spacing in this case is 312.5 kilohertz, or 20 megahertz divided by 64. So the carrier spacing is 312.5 kilohertz. Within each carrier we exhibit flat fading, whereas over the whole bandwidth we have frequency selective fading. So this is the approach that is taken in OFDM in order to combat multipath fading channels. That is, we take the data, modulate them into separate carriers, and at the receiver we receive each carrier, demodulate them separately, and then we get our aggregate high throughput. However, each carrier itself only modulates a subset of the data rate.